and welcome to NASA's Lunar Science Media Briefing for the agency's Commercial Lunar Payload Services, or CLPS initiative. I'm Nilofer Ranji from NASA's Office of Communications. Today's briefing will preview the NASA payloads flying aboard one of the first CLPS flights, Intuitive Machines' IM-1 mission. This flight is scheduled to launch aboard SpaceX's Falcon 9 rocket no earlier than Wednesday, February 14th, 2024. This briefing will highlight the NASA science investigations and technology demonstrations flying aboard Intuitive Machines' Nova C lander named Odysseus. Our briefers today are Susan Lederer, CLPS project scientist at NASA Johnson, Farzan Amzadjarian, principal investigator for the Navigation Doppler LiDAR at NASA Langley, Tamara Statham, co-principal investigator for Lunar Node 1 at NASA Marshall, Danielle Cremens, deputy principal investigator for the Laser Retroreflector Array at NASA Goddard, Nat Gopalswamy, principal investigator for the radio observations of the Lunar Surface Photoelectron Sheath at NASA Goddard, Michelle Monk, principal investigator for the Stereo Camera for Lunar Plume Surface Studies at NASA Langley, and Lauren Amin, deputy project manager for the Cryogenic Fluid Management on behalf of the Radio Frequency Mass Gauge at NASA Glenn. First, we'll start with some initial remarks from each of our briefers before opening it up for questions. We'll be taking questions online, so if you've joined us here today, please press *1 to submit a question and to ask your question. You will be unmuted to ask your question, and once your name is called, please state your name, affiliation, and to whom you'd like to direct your question. We are also taking questions today from our digital platforms. The public can submit their questions on social media using the hashtag AskNASA. We'll now begin with opening remarks from Sue Lederer. Sue, over to you.
Good morning, everyone. I'm the CLPS project scientist for IM-1, so I'm working with all the NASA payload teams and Dr. Deborah Needham, our headquarters program scientist, to ensure that operations maximize the science and technology return from our payloads. First, I want to give you a little overview of what CLPS is all about. The goal here is for us to investigate the moon in preparation for Artemis and really to do business differently for NASA. One of our main goals is to make sure that we develop a lunar economy. For CLPS, we, NASA, hitch a ride on a lunar lander that's developed by commercial industry. These aren't NASA missions, they're commercial missions. These commercial companies will be bringing our instruments along for the ride, enabling our investigations by providing power, data, and comm to us. With the commercial industry comes a competitive environment, which means that our investment up front ultimately gets far more for far less. So instead of one mission in a decade, it allows for more like 10 commercial missions to the moon in a decade. Instead of 4 or 5 instruments in that one decade, it's more like 4 to 5 dozen instruments. Being risk tolerant allows for high yield and high reward, and this is the beauty of CLPS. We'll learn from what does and doesn't work, testing many technologies, conducting experiments at a lower cost and significantly faster than traditional NASA missions. This will allow us to prepare for Artemis more efficiently. When you change the frequency of missions and the risk posture, you change how you do things. Opportunities arise for far more science and technology investigations, a far greater number of places you can go to on the moon, and the diversity of people involved blooms to inspire all future explorers. This is CLPS. The first commercial mission for Intuitive Machines will hold a suite of 6 NASA payloads. The landing site that we're going to is a relatively safe and flat area a little ways from the Malapert 8 crater, about 10 degrees from the South Pole. The South Pole is generally a fairly rough area. This will give our commercial vendor, Intuitive Machines, an opportunity to bring this suite of payloads to an area that'll be the farthest south that any private lander has ever been to on the moon. And it will give us an opportunity to test our instruments in this very harsh environment where the sun is always low on the horizon. The temperature gets quite cold and will help us teach what challenges face us in communicating with the Earth when it's also rather low on the horizon. Our LN1 payload is going to help us learn about communicating from areas around the South Pole like this. The NASA payloads on IM-1 will also test technologies that'll pave the way for how to navigate to and land safely and autonomously on the lunar surface, including NDL, that uses lasers to guide how fast and how close the lander is during landing. LRA that reflects laser light right back to the incoming or orbiting spacecraft with the laser to give future spacecraft a reference point on the lunar surface. LN1 will test technologies that will act like a lighthouse, but as a radio beacon, similar to how you use your GPS. RFMG will measure propellants and fuel left in the tanks to allow for a safe landing, ensuring that we have enough fuel when we land. Scalps will image the engine exhaust turning up dust on the surface. This will expose fresh surface underneath, and the suite of cameras will then continue to image that surface for science investigations. And finally, ROLSes will investigate influences of the sun on the lunar surface, both for science and to help better prepare for Artemis missions, and to conduct radio astronomy for the first time from the moon. All very exciting. Nilofer, back to you.
Thank you so much, Sue. We'll now hand it over to our CLIPS payload teams. Let's begin with Farzan Amzajarian for the Navigation Doppler LiDAR. Farzan?
Good morning. Navigation Doppler LiDAR is a laser sensor that shoots 3 laser beams to the ground and measures a spacecraft velocity, that's the speed and the direction of the flight, and the altitude above the ground. This is when the vehicle begins its descent toward the landing site. So it comes on during the last few minutes of the mission. This is the critical phase that every event, every maneuver, every thruster firing has to be perfectly on the cue. This is those minutes of terror. By providing very precise velocity and altitude data, the NDL enables the spacecraft to navigate exactly to the landing site and help it touch down gently at the intended location. So the NDL will play an important role in the future landing missions as we are moving toward landing in rough terrain and putting the landers at precise locations, perhaps at the edge of a cliff or close to pre-deployed assets. This IM-1 mission will be a great demonstration of this technology for those future missions, including human missions to the moon. Thank you.
Thank you, Farzan. Next up, we have Tamara Statham for Lunar Node 1. Tamara?
Yes, good morning. I'm Tamara Statham with NASA Marshall Space Flight Center, and I'm the co-investigator for the Lunar Node 1 payload. Lunar Node 1, or LN1, is a navigation beacon demonstration. Its goal will be to demo autonomous navigation technologies that are desperately needed to support a growing lunar architecture. As lunar activity increases around the moon, so too will demand increase on Earth-based systems like the Deep Space Network for navigation needs. While these systems provide great capability, the capacity will be outpaced by the number of users. LN1 takes advantage of CubeSat flight hardware. It's a small platform easily integrated into future elements of lunar infrastructure. LN1 utilizes the Multi-Spacecraft Autonomous Positioning System, or MAPS. With MAPS, every lunar element serves as a node in a greater network, and nodes share packets that embed their time and state in a standardized format. With reception of a packet, a node is able to form range and range rate observations from a source that is broadcasting out its local position. In this approach, each asset can become a navigation reference. LN1 will also demo a one-way ranging signal similar to that used within GPS satellites. This enables an alternate approach to determine distances between assets, and when combined with MAPS transmission of position and time, allows it to operate in a similar manner to a GPS pseudolight. LN1 demonstrates one node of a greater network, and then throughout transit and on the surface of the moon, the payload will broadcast telemetry packets to Earth, where the signal will be received by the Deep Space Network, processed, and a nav solution compared against others like that of the IM lander. Future upgraded versions of LN1 will demo two-way ranging, survive the night capability, as well as integration capability with the LunarNet comm and nav infrastructure. Thank you.
Thank you so much, Tamara. Next up, we have Daniel Cremens for the Laser Retroreflector Array. Daniel?
Good morning, everyone. I'm Daniel Kremens from NASA's Goddard Space Flight Center, and I'm the Deputy Principal Investigator for the Laser Retroreflector Array Instrument, or LRA. As you may know, LRA is a completely passive instrument consisting of a hemispherical array of special glass prisms called retroreflectors. What they do is they return the light back directly towards the illumination source. A similar optical phenomenon is used in road markers to make them shine brightly under a car's headlights. On Eclipse lander, however, LRA will act as a precise marker of the lander position, and that will be visible under illumination from either a laser ranging system on board an orbiting or landing spacecraft. Now, LRA requires no power, no thermal control, or interaction with the lander, which allows it to be used for decades on the lunar surface and in the challenging lunar thermal conditions at the South Pole. LRA will be used to geolocate the lander on the surface with high precision, measure any changes in the lander position over long time periods, and determine the precise orbit or landing trajectory of a spacecraft illuminating it. The LRA team is very excited to be a part of the Intuitive Machines mission. Thank you.
Thank you so much, Daniel. Over to you, Nat Gopalswamy, for the radio observations of the lunar surface photoelectron sheath. Nat?
Hello, everyone. ROLSUS is a radio telescope operating in the frequency range from 3 kilohertz to 30 megahertz to observe cosmic and terrestrial radio waves on the moon. The low-frequency cosmic radio waves cannot be detected on Earth due to the intervening ionosphere. ROLSUS will detect the powerful auroral kilometric radiation originating at several thousand miles above Earth's poles. Various transmitters on Earth broadcast wide-ranging radio waves that are also appearing as noise on the moon, adding to any noise generated by the mechanisms on the lander. The sun emits different types of radio bursts that will be detected by ROLSUS. These bursts are caused by energetic electrons interacting with solar magnetic fields. They inform us about the physical conditions in the corona and interplanetary medium, and also about solar flares and coronal mass ejections. ROLSUS will detect intense radio emissions from Jupiter. Such emissions are also known from Saturn, Uranus, and Neptune. The knowledge on planetary radio emission will be helpful in detecting exoplanets using radio telescopes in the future. ROLSUS will measure the electron density and vertical gradient above the lunar surface. These are photoelectrons knocked off from the solar surface by sunlight. The impact of lunar dust on ROLSUS antennas is expected to produce detectable radio signal. These dust impacts are known to peak at the terminator and are responsible for the so-called horizon glow. Finally, the radio intensity of the Milky Way galaxy peaks in the ROLSUS frequency range. Detecting and characterizing the galactic background emission is important for cosmological studies. The ROLSUS instrument on IM-1 is thus poised to contribute to answering wide-ranging science questions. Thank you.
Thanks so much, Nat. Next up is Michelle Monk for the stereo camera for lunar plume surface studies. Michelle, over to you.
Hi, welcome everybody. I'm Michelle Monk from the NASA Langley Research Center, and I'm the principal investigator for the stereo cameras for lunar plume surface studies, or SCALPS. SCALPS is comprised of 4 small cameras mounted near the bottom of the Odysseus lander and oriented so that they can view the surface under the main engine. The cameras will take images during vertical descent towards the moon, through touchdown, and then engine shutdown. They'll continue to take images periodically throughout the lunar day until the mission ends. Using a stereophotogrammetry technique, our team will then reconstruct a 3-dimensional shape of the lunar surface to see the extent of erosion that occurred during landing. The SCALPS measurement is going to provide us a critical data set to anchor computer models for predicting plume surface interaction effects. These effects will be really important to understand as we start to send larger landers to the moon and with humans, and to aggregate assets close together to support a sustained lunar presence in Artemis. Thank you.
Thank you, Michelle. And finally, over to Lauren Amin for the radio frequency mass gauge. Lauren?
Hi, good morning. I'm Lauren Amin. I'm the Deputy Manager of the Cryogenic Fluid Management Portfolio Office at the NASA Glenn Research Center. and I'm here today on behalf of the Radio Frequency Mass Gauge Team, or RFMG. RFMG is one of the cryogenic fluid management technologies in development within our portfolio office. The RFMG and IM-1 will demonstrate a sensor technology that's been in development at NASA Glenn for over the last 15 years. RFMG allows for more accurate in-space cryogenic fuel gauging in spacecraft fuel tanks like those in the IM-1 Nova C lander. Our engineers do this by measuring the electromagnetic spectrum, or radio waves, within the tanks throughout the mission, compare them to a vast fluid simulation database our team's been building, accurately gauge how much propellant is inside those tanks. RFMG has been proven in many ground tests, a suborbital parabolic flight, and also on an experiment on the International Space Station. RFMG's demo on IM-1 will provide NASA for the very first time long-duration microgravity data that will be used to iterate and scale the technology to enable improved spacecraft and lander operations. This RFMG technology is critical and enabling for future long-duration missions that use cryogenic propellants, as RFMG could potentially save fuel and take the guesswork out of spacecraft design and operations in the future. Thank you.
Thank you so much, Lauren, and thanks to our briefers for those initial remarks. For awareness, we also have some additional NASA subject matter experts on the line in case there are specific questions that come up. We'll now open it up for questions. Again, for those of you on the line today, please press *1 to submit a question. And once your name is called, please state your name, affiliation, and to whom you'd like to direct your question. If you find that your question has already been answered, press *2 to withdraw it. Our first question is from Jonathan at Fox News. Jonathan, your line is now open.
Good morning, everyone. Jonathan Seri with Fox News. Thanks so much for doing this briefing. My question's for any of the NASA experts who'd like to jump in. As you look ahead to crewed landings on the moon with the Artemis program, what would you say is the most important thing or the biggest unknown that you're hoping to learn about the South Polar region through the IM-1 mission? Thank you.
Sue, I'll ask you to kick that off. Sorry.
Sure thing. This is Sue, the project scientist for the IM-1, all the payloads. So for the South Pole, it's a really, really harsh environment. And what we have planned for IM-1 really kind of concentrates on this safe landing and making sure that we can also communicate back to the Earth. Sometimes when you're at a very, very low point on the horizon, the communications can kind of bounce along the terrain coming and going. So having a location that's close to the South Pole will help us to start investigating those kinds of things that are happening. LN1 will help us with those investigations. And also, because the environment is quite harsh, it's going to give us a baseline for understanding things like how do solar panels work and how do the instruments function in these very cold temperatures or warm temperatures when the sun is shining on them. So I think it's a very good place to start, having some slightly more straightforward payloads that investigate how the South Pole acts, what the environment is like, to help us with future missions.
Perfect, thank you. Our next question comes from Will Robinson-Smith from Spaceflight Now. Will, your line is now open.
Yes, hi, Will Robinson-Smith with Spaceflight Now. Thank you so much for taking the time to answer our questions. One to Lauren and Amin, if I could. In the data that you'll be getting back from the radio frequency mass gauge, is the intent to, not just for, future CLPS missions, but for the Human Landing System Program, lander, contractor, SpaceX, and Blue Origin principally, is the goal to share that data with them to help better inform some of their cryogenic propellant transfer, both demonstrations as well as the actual performance thereof during the Artemis missions that they're a part of? Thanks.
Hey, yeah, this is Lauren. So the opportunity to understand and demonstrate RFMG during most of the transit phase of the Odysseus lander is going to give us an opportunity to understand how the data correlates with what I talked about, that vast fluid simulation database, which is really how we estimate how much propellant is in the tank. Like all the other space technology projects at NASA, we absolutely intend on improving our data and sharing that with all of our commercial partners, not just those for HLS. So hopefully that answers your question, but absolutely, I think the intent is to infuse this RFMG technology into all future missions where that makes sense, to really try to improve our cryogenic fluid management capability.
Thanks, Lauren, and thanks for that question. We're now going to hear some questions we received from our social media platforms using the hashtag AskNASA. And our first question comes from Instagram, and it was, what type of fuel is the lunar lander using? Sue, I'm going to punt that question over to you to respond to.
So we're going to be using both liquid oxygen and liquid methane. These are both cryogenic fuels. And I'm actually going to pass that right back over to Lauren because their team is working very closely with Intuitive Machines on their liquid propellants.
Hey, Sue, yep, you're correct. Liquid oxygen, liquid methane. And I'll just say, too, that our RFMG team has been working with the IM-1 team over the last week during their wet dress rehearsals, and those have gone really well. And so we've proven out that our RFMG payload is working.
Perfect. Thank you both. Our next question from using the hashtag AskNASA comes from Facebook, and that is, how much space or mass does the lander or the payloads take up? So for this purpose, since we are looking at the NASA-provided lunar payloads, let's talk about how much mass the NASA payloads take up on IM's Nova-C lander. And I will give that one to Sue, sorry.
Yeah, so I think we actually have Chris Colbert in the room, and he might actually know the answer to that question off the top of his head. I do not.
Sure. So it's in the range of 40 kilograms. For the first two missions that CLIPS sponsored, we were a little on the lighter side. You'll probably note that our later missions are closer to 100 kilograms. But for IM's first mission here, it's close to 40 kilograms of NASA payloads.
Thank you both. Now we'll go back to a couple of questions from the media. Next up, we have Bill Harwood from CBS News. Bill, your line is now open.
Hey, thank you very much. I have two quick questions. One for Michelle. Is the payload primarily just to demonstrate the technology and show how it works, or do you expect to actually learn something about the soil in that region? In other words, what are you expecting from that soil at the landing site? And the second question, I think, is for Susan. I'm sorry, not for Susan. Let me get my name straight here. I'm sorry. For Lauren. Can you give us a little more info on how the testing worked? I mean, I don't know when they fuel your spacecraft during the countdown, or how any of that works. We don't really have many details about that. Thanks.
Okay, this is Michelle. I'll take the first part of that. Thanks for the question. This is actually both a technology demonstration and hopefully some use for science. I guess I'd call it more of an engineering measurement, but we are really excited about the opportunity to go towards the South Pole because that is an area, as Sue mentioned, that we haven't landed in before. So we have the video from the Apollo landings in the Mare region where you see, lots of dust blown around, thrown out from the base of the Apollo landers. And we really want to see if the behavior is similar at the South Pole. Now, granted, this Odysseus lander is a much different scale than Apollo or from the landers that we intend to send in the future. But this starts us on the path of both demonstrating that this instrument can make a measurement and getting some early knowledge about the South Pole regolith and how it will behave. So I hope that answers it. Thank you.
And if I can just step in real quick, this is Sue, and one of the things that we at NASA do is when we have instruments that are designed to gather data that can be used for science, We have something called the Planetary Data System, which is online where the images and the data, such as what SCALPS is going to be collecting, is actually archived for future use for scientists to continue to use that data to understand better what the surface of the moon is like in this case. And this will be archived with the PDS. And I can tell you that, at least from my past as an astronomer, using images to study different types of astronomical bodies, the images themselves can be used to really dig in when you see the very close-in features. And so I expect that we're going to get some really good science out of the imagery that's coming back from SCALPS, without a doubt.
All right, and this is Chris Culbert. I'll hit your second question about the ground ops for the LOX methane. So this is the first time we've flown LOX methane off of one of the old shuttle pads, 39A. So it did require some modification to the shuttle pads to allow the SpaceX to fuel the lander while it's on the pad. And because these are cryogenic fuels that will boil off if they get too warm, you put that fuel in pretty late. So right now, we expect they will start fueling both the tanks on the lander about 3 hours before liftoff. And it takes a couple of hours to fill the tanks up. You want to make sure that they maintain the right temperatures all the way through that load process, and you have to get the right temperature before you can launch. But they've run a couple of wet dress rehearsals over the last week to demonstrate all that systems that have all worked very well. So we're looking forward to a very successful launch this week.
Thank you all. Our next question comes from Gina Sinceri at ABC News. Gina, your line is now open.
Thank you. This question is for Farzeen. I'm interested in the LIDAR experiment. How important are lasers becoming in this kind of exploration?
Okay, yes, this is Farzin from NASA Langley. That's a tough question. As we are looking into these more challenging, more ambitious landing missions, LIDAR and laser is going to be playing much important role as we're going forward. The navigation Doppler LIDAR that provides the velocity and altitude, it's sort of, you can think of it of a replacement of the radar sensors that were used before. But the precision of this laser sensor is at least an order of magnitude greater. So the quality of data, the precisions will really help this landing vehicle to navigate more precisely toward the landing site. So this is just one aspect. We are also looking at LIDAR for doing hazard detection on the landing. That is, once we are reach the landing location and we are starting to do a vertical descent, we want to be able to map the terrain and figure where the hazards are and make sure that the lander does not land on a piece of rock or a crater hole, and that's another area that the laser and LIDAR can play a critical role. Yet there is another application for the lasers that are being looked at, and that is terrain relative navigation. That is when we are way up, maybe 20, 30 kilometers above the ground, using the laser to look at the features terrain below and look for known features like a known crater to give us a good position information. I'm sorry for touching all these technologies, but let me summarize them. So when we are coming down, let's say we're going to the moon and we are starting at 20 kilometers above the ground and we are kind of horizontally or at a slanted path going down, the laser can look at the terrain below to find known features so we know where we are. Then we have the navigation Doppler LiDAR that's going to be demonstrated on this mission to provide very precise velocity and altitude data for the vehicle to navigate precisely to the landing site. And once we get there, a laser can scan the ground below and um, so we can avoid the hazards and land the vehicle between, rocks and craters precisely. I hope that answers your question.
That was great, Farzan. Thank you both. Thank you so much. We're going to switch gears for a moment and go back to questions on social media using the hashtag AskNASA. From Instagram, how will the lander or the payloads recharge? And can the lander rotate to face the sun? I'm actually going to ask Chris Colbert, Program Manager for CLIPS, to answer that question. Chris?
Sure. So, recharging is done through solar arrays. So the lander will have solar arrays on it that will capture energy from the sun, turn it into electricity, and pass it on to the payloads. During transit to the moon, yes, the lander will rotate or adjust its attitude so that the solar arrays get the right amount of sun on them so it can generate power. Once it lands on the moon, no, it's landed and it doesn't move anymore. The solar arrays are not on gimbals or mechanisms that let them change their direction. So Intuitive Machines has spent a fair amount of energy analyzing where they're landing, where the sun's going to be, and how the sun will cross the horizon during the portion of lunar day that they're there. And then they design the lander arrays canted such that they capture the right amount of sunlight to generate electricity.
Thank you, Chris. Our next question from social media is about lunar dust. So is moon dust analysis planned? And I think I'm going to turn that over to the SCALPS team that's on the line.
This is Michelle. I'm not quite sure about moon dust investigation. Back to the answer that Sue provided, I think, close-up imagery of the regolith particles will be very instructive going forward. Our cameras will have fields of view that have lander surfaces in them so that we can see over time if the dust moves around and how it clings to different surfaces. And we hope to make measurements like this on future landers so that we can start to build up more knowledge of the dust behavior. Thanks.
Yeah, this is Chris Colbert. I'll add a little bit to that one for Michelle. So this mission in particular is mostly capturing imagery, which will tell us how dust behaves when it's blasted during the descent and how it will move around, as Michelle just described. On some future missions, we'll have some more advanced experiments which actually take a look at how dust interacts with materials and surfaces, but that won't be on this first mission. Those are going to be in some future missions.
And if I can just add in that there's one other sensor that we have on board, and that is Rolls's has 4 radio antennas, and one of the modes that they have for collecting their science is to actually detect dust as it impacts the antennas. So Nat, I don't know if you want to speak a little bit about that capability, but that can also help us understand the dust, how it charges up, and help us to design future spacesuits as well to figure out how to minimize the dust clinging to the suits. Nat, do you have anything to add?
I would like to add that the dust impact actually increases at the terminator so we may have to do some operations in the night to understand more about this dust. So the basic detection mechanism is that dust hitting the antenna will produce a small voltage signal. Thank you.
Thank you all for responding to that question from social media. We'll now switch it back to questions from the media. First up, we have Kenneth Chang with the New York Times. Kenneth, your line is now open. Kenneth, can you hear us? All right, we'll go back. Let's go over to Jeff Faust with Space News. Jeff, your line is open.
Good morning. 2 quick questions. One for Farzan. What sort of landing accuracy can the navigation Doppler LiDAR provide? How does it compare, for example, to what Japan's SLIM lander achieved last month? And then for Susan or Chris, are there any special coordination issues among the payloads to ensure that they all get the power and communications that they need at the various phases of the mission? Thanks.
Okay, This is Farzin. I answered the first part of your question. So navigation Doppler LiDAR, like I mentioned earlier, can provide very high precision velocity and altitude data, better than the order of magnitude better than radars. Now, in terms of the precision landing, that really depends on the vehicle itself, how it's going to use this data to improve its precision. And that really depends on the landing vehicle, and I cannot really comment about, for example, this IM mission is coming up. I do like to add that IM-1, the Nova-C vehicle, does, on this mission, does use the NDL data to help it with improving its precision landing. We are not a primary or critical sensor on the vehicle, but the data is used to help with that precision. And in terms of how precise is that, then it's really an IM question.
So as far as on this covered, I'll add a little bit to that. NASA's requirements for this mission weren't very challenging for the very first landing on the moon. IM has told us they believe they'll have accuracy in the 100-meter range, which is comparable to the SLIM mission from Japan. But we're not really pushing that as a high priority of this mission. We'll have some future missions which will require at least 100-meter accuracy.
Thank you all. Let's go back to Ken. Sorry, Sue, do you have anything to add?
Oh,
yes,
that was me, Farzin, actually. Since we are talking about future missions, I'd like to add that with the laser LiDAR technology, it is possible to get these precisions to meters regime. Like I mentioned, with the terrain-related navigation that is looking at the terrain features with the laser beam, getting a very good position knowledge and the navigation Doppler LiDAR to navigate to that location, and scanning the terrain for known feature again upon landing, we can get down to meters type regime. When we did demonstrations here in the past using LiDAR technologies about a decade ago, we got down to about 10 centimeters. So this type of precision is quite achievable. Thank you.
And just going back to the question about coordination with the payloads, this is an excellent question, and it's something that we've been working on for quite some years with both our individual payload teams coordinated with Intuitive Machines. We have 6 payloads on board. They have 6 additional commercial payloads on board as well. So in the years leading up to the operations, we ensure that we have what our requests are for what our payloads need for operating to Intuitive Machines, and then we coordinate together with timeline tools. NASA Ames has created a great playbook plan and they have a timeline tool as well where we put all of our plans for when each of the payloads are operating so that we can see a full coordination to ensure that the payloads don't interfere. And then as well, when payloads can run in parallel, that we maximize the amount of science return by allowing payloads that can autonomously take data, continue taking data, while other payloads need to have kind of a step-by-step interaction with their payload to collect data coming back. But this is all very well coordinated, and the plan has been in place for some time, and so I expect that we're going to really maximize the science return.
Thank you so much all for responding to that question. Let's go back to see Ken Chang from the New York Times. Your line is now open. Ken, can you hear us now?
Yes, great. Thank you. Sorry about messing up earlier. I was wanting to ask about the landing site. It was moved to the South Polar region, and we've heard about wanting to learn about the regolith in this area, but I was wondering what other science you might be able to get from being here versus the original landing site. Thank you.
That's an excellent question. So this particular landing site is a very old terrain, and so this terrain is For the geologists on board, it's more of a standard feldspathic kind of highlands, and it's similar to the Apollo 16 site. So it tells us a little bit more about the original crustal materia from when the lunar magma ocean cooled, and of course, being beat up by impacts for billions of years, covered up by the impact ejecta, can allow some of the material underneath to then surface. So all of this information can help our scientists better understand a little bit more about the highlands of the moon, and then be able to compare it to the Apollo 16 site from the science side.
Thank you. Next up, we have Leonard David with the Scientific American magazine. Leonard, your line is now open.
Okay, thank you. For Michelle, going to the South Pole, we haven't been there. What kind of modeling has been done about the dust that you may or may not run into there? And the other question would be for Dan on the LRA. You've got SLIM has an LRA on it, and the Indian spacecraft. So are those active? Are you doing some experiments with lasers from LRO, or what's the status there? Thank you.
Hi, Leonard. This is Michelle. Thanks for the question. We hope to learn quite a bit about this new area. In terms of modeling, we have, the lunar source book as our source of regolith data from Apollo. And, of course, there are some, unknowns in there about, different phenomenon, different characteristics of the regolith in regions that we haven't actually directly measured yet. So, compaction and everything comes from just scientific observations, and so there's quite a bit of uncertainty on different parameters that we would use in a model to predict the amount of cratering or the amount of regolith that's ejected from under a lander, and how big the particles are and how far they would go. So those are all the types of effects that we're trying to capture. We will not capture them all with scalps. It's merely a optical measurement of what the surface looks like after we land. On future landers, we hope to add more types of instruments that can build upon scalps and measure the ejecta itself, as well as effects on the lander surfaces, like the lander base. So those are future plans. Our models are pretty immature, I'd say, at this point, or unvalidated, because we haven't measured these phenomena directly before. What we really want to do to understand this completely, it's going to vary with each location somewhat, and with each lander size, mass, engine configuration. And so having that predictive model that can span all of those different cases is going to be, the key for really predicting what's going to happen on future flights. So in order to get that, we want to make these in situ measurements at the moon, like with scalps and future payloads. We also want to conduct ground testing where we can carefully control the parameters and investigate, a wide parameter space to try to get a validated model. Thanks.
And this is Daniel Kremens for LRA. Thanks for the question. We are indeed continuing to range to the two LRAs currently on the surface from the Chandrayaan-3 mission and the SLIM mission. As you know, the SLIM lander is at a non-optimal attitude for how we plan to use LRA, but we do still think that we'll be able to range to LRA in its current kind of off-nominal configuration. And the orbit of LRO at the moment allows us to attempt to range to each LRA about once every 2 weeks or so. And so we will continue to do this, as long as LRO and the laser altimeter on board is operational. And I'd encourage you to, Next month at the Lunar and Planetary Science Conference, the LRA PI, Dr. Shaoli Sun, will be giving a presentation on the ranging results to Chandrayaan-3, and we'll also update on any results that happened essentially from January until March. Thanks.
Thank you. Next up, we have Alexandra Witz from Nature Magazine. Alexandra, your line is now open.
Great, thanks very much. My question is about ROLSs, so it's for Nat. Could you talk a little bit about the sources of interference expected? I mean, the Chinese had that lander on the far side where they were trying to do radio astronomy and got a lot of interference from their lander. What are you anticipating in terms of interference, both from the lander itself and then also, of course, being on the near side instead of the far side?
Thank you for the question. For the near side, the main interference is actually, as I mentioned, is from the terrestrial transmitters. And these are expected and have been detected, once or twice when the wind spacecraft was closer to the moon. And these appear as horizontal lines in the daily spectra we take, and therefore it's easy to identify these interferences and then still subtract them out to get the real signal from, for example, the sun. So that is definitely, a very horizontal straight line, so it's easy to extract. Now, for the lander, this is one of the things that we do not know. We are going to characterize them. So that is actually completely unknown at this stage.
Thanks for the question. The next line we have is Jim Siegel with NASA Tech. Jim, your line is now open.
Oh, thank you for taking my question, and good luck on this particular mission. I'm curious, I understand that there are about 6 or 7 other CLPS missions that have been planned or are on the books. And I'm wondering, are they all going to go to the same location, and are they going to build on each other in terms of knowledge, that is, one builds on another? And suppose 1 or 2 of them don't make it. Is that going to endanger the timing on Artemis 3? Thank you.
Okay, this is Chris Colbert. I'll take that one. So yes, we have a number of missions. I think we're up through 9 scheduled to the moon at this point. They are all going to a variety of locations, mostly driven by the science that we're trying to achieve. You can't do the same science at every spot in the moon, so the objectives of the payloads tend to drive where we take them. We are having a number of missions that go to the South Pole because, of course, that's of high interest to future human exploration. And there is complementary science across the missions. As we learn things from one mission, we'll be able to help calibrate and prepare for future missions more effectively, so we are certainly doing some of that. But none of our missions are directly linked to Artemis 3 or the planning for Artemis 3. The data we gather will help agency plan better for all future Artemis missions. But if we lose 1 or 2, which was what CLPS was intended, or we knew could happen, it won't endanger the Artemis missions, the Artemis planning.
Thank you, Chris. Our next question comes from Will Robinson-Smith from Spaceflight Now. Will, your line is now open.
Yes, hi, thanks for taking another question from us. Follow-up, if I may, to Bill Harwood's question from a little bit earlier to Chris Colbert. Can you provide a little bit more detail regarding the WDRs and how they performed, if there were any leaks that came up or any other issues? And another quick follow-up, what are the T0 liftoff options for the backup windows on the 15th and 16th? Thanks.
So on the wet dress rehearsals, you probably have to ask SpaceX about that. SpaceX and True Machine actually ran those. Those aren't NASA functions. And sorry, we missed the second part. What was your second question?
So just if you have the T0 for the backup dates on the 15th and 16th.
Actually, I don't have those handy. We think that'll be coming out in something later on this week, but I don't have them handy with me right now.
So with regards to launch windows and timings, we recommend that you reach out to the launch provider, so in this case SpaceX, for responses on T-0 for the other launch opportunities. So thanks to all who submitted questions today, and thanks to our briefers for taking the time to discuss NASA's CLIPS initiative and their payloads aboard Intuitive Machines' IM-1 mission. As a reminder, SpaceX is targeting no earlier than 12:57 a.m. Eastern on Wednesday, February 14th, for a Falcon 9 launch of Intuitive Machines' first lunar lander to the moon's surface. We appreciate you joining us. A recording of this briefing will be available on nasa.gov/clips. That will wrap today's briefing. Thank you.